People have gotten lax on that. And I have too. Okay, so rewriting this equation right here, if the total entropy's derivative with respect to the number density or the number of particles in one system is extremized, then we can rewrite this condition right here just as saying that the two slopes of either of the two systems we're considering here are equal to each other at equilibrium, right? So that's the exact same thing we did with volume and the energy before. So now what we're going to do is we're just going to slap on a, okay, I'm just not going to write in like, where's the dead zone? It's like right here. I'm just not going to write in that area. That's annoying. Okay, so we're going to slap on a minus t to each side of that. And obviously the equation still holds. And we're going to call this a new thermodynamic quantity. We're going to define this to be the so-called chemical potential. We'll define it to be minus t times that slope, holding the energy and the volume constant, such that mu A equals mu B at equilibrium. Okie doke. So, let's see. So basically, now that we're allowing the number of particles to move around, if the slope of one system or the other is bigger, so if system A, so let's say like system A, Jesus, okay. System A has larger, let's say more negative, mu A greater than mu B. So the slope here is larger than system B. So which way do we think particles will flow between the two systems? Anybody have any thoughts about that? So will it flow from B to A or A to B? Let's think about this, right? So if its slope here is bigger, that means that mu is bigger, more negative, right? So if it gains a particle, it'll increase a lot more for A versus increasing or decreasing for B. So if a particle moves from B to A, then this entropy will go up because the slope is bigger for A. So it's a little backwards because we're throwing a minus sign on here. But always think about it in terms of the slope right here, the slope of the entropy with respect to whatever thermodynamic quantity you're talking about. So if a particle moves from B to A, the entropy overall will go up. And so therefore, if the chemical potential of A is bigger in like an absolute sense, I guess I should say, then it'll move from system B to A. But since there's this minus sign, in general, you're going to be going from like a slightly like more positive negative number here to a much larger negative number over here. Does that make sense to everybody? So it can be a little, you can get a little tripped up conceptually because of this minus sign, but just always think about it in terms of the slope right here and maximization of energy or entropy. All right. So yeah, we went through that. So yeah, the system is always going to seek to reduce its chemical potential is what we'll say, because it's always going to go to the one that is more negative. All right, so at this point, we can generalize the thermodynamic identity. Now incorporating our notion of the chemical potential. So let's have a change in entropy, where first we have following. We have delta U goes to U plus delta U. We have, sorry, just a U there. V goes to V plus some delta V. And we also have the number of particles goes to N plus delta N. So before we derive the thermodynamic identity by just taking these two right here, now we're just throwing on another and doing the exact same thing. So now the total change in entropy is going to just be the sum of all of the smaller changes in entropy. So it'll be process 1, which we'll call this, call that 2, call that 3. So you just add them all up. 2 plus delta S 3. And we're going to have to go to another page. Oh, yeah, I'm going to run into that again. Apparently I need to get a new tablet already. Okay, so now we're just going to do the same thing that we did before. We're going to multiply by 1 a bunch of different times. So on the first term over here, we're going to multiply by a delta U over delta U. Here we'll multiply by a delta V over delta V. And here we'll multiply by a delta N over delta N. And then we will rewrite that as delta S over delta U, holding V and N constant, delta U, plus delta S over delta V, holding U and N constant, delta V, plus delta S over delta N, holding now U and V constant, delta N. And so now we just take this, turn it into its differential form, and we have that ds is equal to del S over del U, V and N held constant du, plus del S del N, sorry, del V, U and N held constant dV, plus del S del N, U and V held constant dN. All right, so now at this point, we just do the same thing that we've done before, and we just substitute in our definitions for all the different thermodynamic quantities. So here it'll be in terms of temperature, here it'll be pressure and temperature, and here it'll be chemical potential and temperature. So using our definitions, this becomes 1 over T du, right? That's just 1 over the temperature. This is just the pressure over the temperature, dV. And this right here is just minus the chemical potential over T, dN. And now if we do a little bit further rearranging, we can get this into the form of the full thermodynamic identity, which is just du equals TdS minus PdV plus mu dN. And you notice this is the exact same thing we had before if n is constant. So basically now how you can think about this is that the change in energy can be broken up into 3 different terms if we allow entropy to change, the volume to change, and the number of particles to change. So this term we can think of as the heat. This term you can think of as like the mechanical work. And this term you can think of as like a chemical work. And now, if you just remember this single identity, you can rederive all of the different thermodynamic relations that we've talked about so far. So you can easily remember what the relationship for T is. For example, oh, I see something in chat. Yeah, Jerry, what's your question? Shoot. Yes, that is exactly what we assumed back here. Yeah, so when we looked at this, we took one step where it takes U to delta U, V to delta V, and then N to delta N. Each of those steps is with the others held constant while you do those changes. And that's why we have these stipulations right here. So like this is V and N held constant. Yeah. What's not true? That is accurate, yeah. I mean, here, well, I mean, you can't necessarily just say that for a single object it won't be true. What will be true will be dependent on like the process that you're using on that object, right? So, I mean, it's not that this is just like false for an ideal gas, and in fact, you can show that it just recovers the ideal gas law, like we did previously in the last class. So, I mean, it just depends on the conditions that you're stipulating for your system. So if you take a system and you act on it in this way, this relationship is true. It's not that this relationship holds for some object or another. It's just that it holds in general if you go through this process. Does that make sense? Still a little uneasy? That's fair. So yeah, hold on to that uncertainty and hopefully it'll go away as we work through problems or something like that. Okay. But I mean, do you at least agree that if we do go through this process where you break it up into 3 different steps and you hold all the others constant during those steps, that you can derive this relationship, right? So yeah, I understand your uncomfortability potentially, but I do think that hopefully it'll go away as we work with it. Because I mean, you can take an ideal gas and you can go through these kinds of steps. Okay. All right. So yeah, let's just play around with this just a little bit to see how we would use it to remember the relationships between thermodynamic identities and their derivatives on the entropy. So for example, if we hold U and V fixed, then we can say this is just going to be TdS, V is fixed, so dV is 0, du is 0 since U is fixed. That this will be plus mu dN. And so if we move stuff around, you can show that the chemical potential is just what we said previously. U and V fixed. If we hold the entropy and the volume fixed, then what happens? Well, we've still got du on the left-hand side. Now this term's 0, this term's 0, and we just have mu dN. So this is a new interesting thing. That mu is also equal to del U over del N with S and V held constant. And we can use this relationship to determine what the units are for this chemical potential right here. We could have determined it before, but this is just a little bit nicer. So does anybody have any thoughts, like from this relationship, what do you think the units are for the chemical potential? So look at the units on this side, they have to match the units on that side, right? So the units for the top are what? Let's see, I got a chat. We have J, joules, yep. What about the bottom? Empty set, yeah. I like that. Unitless. Unitless is right. So this is just units of joules. So the chemical potential is just measured in joules. So basically what the chemical potential is it's the amount the energy changes when you add a particle to a system while holding the entropy and the volume constant. And you can see that specifically from this relationship right here. We just said that S and V are held constant. Therefore, you can relate mu to this partial derivative here. And if we sheet a little bit and turn these partial derivatives into like finite deltas right here, you can just see that the change in energy, delta U, and then move this over to the other side, times delta N times mu is just equal to this delta U. And so therefore, this is just the coefficient which tells you how much energy is changing when you either put particles in or take them out. So let's just demonstrate how that works quickly. So let us consider an Einstein solid again. And let's take N to be 3, Q to be 3, and let's do what we were just talking about. Let's hold S and V fixed. So if we start off with a system like this, we'd have that the multiplicity, 3 comma 3, can just be written as the following. So it'll be N plus Q minus 1, so 3 plus 3 minus 1. And then Q down here, which is 3. This just becomes 5 factorial, 3 factorial, 5 minus 3 factorial. Calculating that out, we would just get 10. So that's what it has initially. Now let's say we take n, and it goes to n plus 1. So in this case, it would be n prime equals 4. So we add another oscillator. Obviously, this isn't very realistic because how the heck do you add an oscillator when typically Einstein solids are thought of as like particles existing in 3 dimensions, each with 3 oscillators. So adding a single oscillator doesn't necessarily make a lot of sense, but this is just the theoretical construction, so we can do whatever we want. So let's do that. And now we see that the multiplicity becomes 4, 3, and this becomes 20. So up here, if we use this to calculate the entropy, we would just write S equals K ln of omega, which is K log of 10. And so we've said that the entropy should be fixed throughout this process when we add a particle. And so we show that naively, if we calculate the entropy initially and the entropy finally, that we get K log omega, which is K ln of 20. So there must be something else going on here, right? Because we're saying that we need the entropy fixed, so when we add a particle, something needs to happen. Well, what needs to happen specifically is that the chemical potential needs to be taken into place here. So another way to think about going from this entropy to this entropy can be thought of as just adding 1 unit of energy. So basically that delta U is equal to epsilon, if epsilon is like the unit of energy that we're talking about here. And if we add a particle and we use our notion of chemical potential, then we should say that if S and V are fixed, that the chemical potential is just going to be equal to the change in energy all over the change in, eraser, the number of particles with S and V held constant. So in this case, we see that if we can think about this change as just being a change in energy unit of 1, then this mu right here should just be minus epsilon. And therefore, we can show that we can actually keep S and V fixed if we take into account this chemical potential. So in this case now, ds is equal to 1 over t du plus p over t dv minus mu over t dn. And we've said that S should be fixed, so this whole thing should go to 0. And obviously V is fixed, so that's automatically 0. And so if we know that this is just minus epsilon, and this is, I think I actually flipped these around. This should be plus epsilon, because it's just adding 1 unit of energy. And this is minus epsilon. Did I mess something up here? I did. This should be a minus. Then this whole thing just vanishes. What did I do? Oh, duh. Yeah, there's a minus sign here, right? Yeah. So this is just a minus epsilon, then therefore mu is minus epsilon. So then this whole thing is equal to 0 if we take into account the chemical potential. So that's just a quick example of how to use this and how the chemical potential balances out the change in energy via adding particles. Okay, so another thing we could do is we could consider monatomic gas, specifically an ideal gas. And for that, we have the so-called Sackur-Tetrode equation, which just looks like the following. Log of V 4 pi mu, this big long thing, 3 Planck's constant squared to the 3/2. And in the past, we normally wrote, there's like an extra 1 over n over here. In this case, we pull out that 1 over n looking thing, and it appears over here. So this is actually the same equation that we've written before. It just looks a little bit differently because we pulled this off. just in case you were worried. So now we have that if we take the definition for our chemical potential, which is minus T times the derivative of S with respect to N with U and V held constant, and we do a little bit of manipulation and apply the aproptotion theorem in here, which I won't go through all the steps for that because this thing's obviously a little bit messy. We get minus KT ln of V over N all times 2 pi mkt over Planck's constant squared to the 3/2. So if we were to, for example, put in helium was the example that Schroeder used, and you substitute in all the proper values at like atmosphere and room temperature, so T is equal to 300 Kelvin roughly, P is equal to 1 atmosphere, and at these two values you could look up what the density is for helium particles at this atmospheric pressure and room temperature in a table, and you could see that V over N is approximately 4.2 times 10 to the minus 26. Obviously it takes up very, very little space per piece, so this is per particle, but particle is dimensionless. I just put it there just so you're aware. But yeah, if you take all of that and you plug it in, you can show that for helium at least, the chemical potential is minus 0.32 electron volts. So that's a typical value for the chemical potential for the types of gases that we're going to be talking about here. And another thing to note here is that since this chemical potential manipulates out to something that looks like this, and you see explicitly the V over N term right here, you can look at that and you can think about how scaling the concentration, the V over N, so increasing the number of particles while keeping the volume the same, will change this chemical potential right here, right? And so if we decrease this effectively density concentration right here, it's going to make mu less negative. It's therefore we're going to be more willing to give up particles, which makes sense because as you pack more and more and more particles into something, you would expect that it's often going to be more likely that these particles are just going to zip off because they're so packed in there, they want to get away from each other. So this chemical potential is going to get very, very small, and therefore it will be very willing to give up particles, right? Because chemical potential has the kind of like opposite idea as the other thermodynamic quantities. So hopefully that relationship between the chemical potential and the density makes some intuitive sense. And another thing to note is that at least here we've only been talking about like a single type of particle at a time. But if we do have like multiple species of particles, like if you've got helium, you've got argon, you've got neon, you've got xenon, like down the list, you would have each of these species would have their very own chemical potential, which is just written in the usual way. All of the previous derivation goes through. But in this case, the things that are held constant would be U, V, and the number of particles for whatever other species. It could be like N2, N3, on and on and on. Just hold all of the others constant. This is the definition for that one. And then likewise, if you have another species, just the same thing, del S, del N2, and then with all the others held constant. And so then the thermodynamic relation just becomes TdS minus PdV plus sum over I. It extends pretty readily. So you just sum over all the different species and how much each of those species is changing in its particle number. So yeah, this is just a brief overview of how the chemical potential is defined, how it works a little bit. Note that the chemical potential is going to become much more central to things like phase transitions and like actual chemical reactions. So we'll get into this a little bit more deeply in next couple of chapters when we actually start talking about chemical reactions and whatnot. But for now, it's just kind of a definition that we arbitrarily imposed on the slope of the entropy with respect to the number of particles. We used that to derive a generalized thermodynamic identity, and we related the chemical potential to the amount of energy that a particle carries as it enters or exits a system. So that's that. Any questions about that? Okay. So that ends the content of chapter 3. So congratulations, we are through the first 3 chapters of the book. And now chapter 4 is going to feel a little silly because it's literally just going to be a discussion of heat engines and a discussion of refrigerators, and then that's it. We're going to leave off all of the stuff that talks about like real life heat engines and the way you would make like real life heat engine processes and whatnot. We're just going to talk about the most ideal case and understand the theoretical underpinnings for how heat engines and refrigerators work. So we'll start to get into that a little bit right now, and we'll probably be able to finish it up next time. And next time we might even start to begin chapter 5. So if you have time in between today and Friday to start reading chapter 5, please do that, because chapter 4 is really not very long. Keep forgetting about